In this video, we will start with Chapter 1, titled Power Functions as Building Blocks. Before we start discussing what power functions are, I just wanted to motivate a little bit why one would care about power functions at all. Well, in its essence, calculus is a study of change, and change most visibly occurs through time. So here is the change that I've been noticing recently. This is the very first picture of my daughter. This was about 4 years ago. She has since grown. She's become a baby and then a toddler. This is earlier this year when she had just turned 4. Through different times of her life, during physical examinations at a pediatrician's office or during an ultrasound, doctors would be interested in different types of measurements to ensure that she was growing at a proportional rate, at an appropriate rate. So when she was still a fetus, at an ultrasound, a technician would measure something like a big visible bone, like a femur, or a distance between a tailbone and the top of her head, as something that they can input into the machine as an actual measurement. Once she became a baby and then a toddler, it was a weight and a height with respect to time or with respect to each other that were the measurements that the doctors were tracking. Now, as a mathematician, I know that all of these things, because of the vast amount of data that we already have gathered on how children grow, are actually modeled with different types of functions. So, for example, these are the functions for femur length, for height, and for weight. I'm not giving you the domains for them here because this is purely for motivational purposes. So let's just take a look at what these functions actually are. Notice that there's no trigonometric functions, there's no exponentials, there's no logarithms. All of these functions are simply the independent variable, so time for the femur length, to some power, so cubed, and then there's 1 here with potentially a coefficient in front of it. Same story goes for the height function. If you just give me time, which means like how old the baby is, this function will give you an average height of, this one actually describes an average height of a female child t months after 12, right? Notice that the weight function here is slightly different from the first two because it's not dependent on height, but on time, but rather on height. And that makes sense too, because of course different genetics will dictate different rates that children grow in terms of height. My child is never going to be very tall because I'm not, and neither is her dad. But a tall child will of course weigh more than a shorter child of potentially the same age. So these functions are once again very simple independent variable to some power with a coefficient in front of it. And those are exactly what we call power functions. Power functions are functions of the form kx to power n, where n we will first consider to be a positive integer and k is some non-zero constant. In order to first visualize what they look like, it would be really nice to be able to sketch just a few of them, right? So for the very first simplest example, we're going to take this k to be 1. So essentially you can pretend it's not even there. So we will consider functions of the form x to some power. And let's take different powers. So for example, x squared, x cubed, x to the 4th, and so on. Now, of course, you can sketch them by hand, but having a computer at our disposal means that we can actually play with different graphing calculator tools. I would like to introduce you to one of the tools that's going to be extremely helpful throughout this course, which is called Desmos. Desmos is a graphing calculator, an online free graphing calculator that you can use much like you would use an actual graphing calculator. So let's take a look here. I'm going to type this in with you. So what I would like to draw is y equals x to some power. And what I'm going to do is not actually specify the power first, but I'm just going to say x to power n. Just like on my slide, I actually wanted to see different powers of n. And the calculator itself will offer, notice on the left side here, will offer for me to add a slider for n, which I will agree to, and it will just give me a way to draw for different values of n, all at the same time as like a little animation. Here I can pick, let's say I want n to be from 1 to, let's say, 10, and I would like step size 1 so that it only goes through the integers 1, 2, 3, and so on. Right? So let's see what happens. This is what my little animation now looks like. I can stop it at any time to just actually take a closer look at what I'm getting. So at n equals 1, we have y equals x. Just a straight diagonal line, nothing too surprising here. At n equals 2, we have a familiar x squared parabola shape. For n equals 3, we have a cubic shape that I sometimes call a snake shape. For n equals 4, we're back to the parabola shape, except for it's a little bit wider at the bottom and grows a little bit faster at the top. For n equals 5, we're back to the snaky shape, but again, it's a little bit flatter than the cube before it, and so on, right? And so notice as I go through that the shapes go between parabola and the snake shape. Those are the only shapes that you will see in terms of power functions that have coefficient 1 in this case too, right? So if I actually draw all the even functions first, you will notice that all of these guys have parabola shapes. You will notice that they're slightly different. So again, like they become flatter at the bottom, and they have this one common point of intersection, but they all have parabola shapes. Whereas if I now sketch all of the odd functions, we will see that all of these have the same snake shape that the cubic one has in the first place. Okay, so let's go back and actually record this observation on our slide. So in terms of power functions, these are the two main cases that I will always witness. Now, what about the second question here? What about if I fix a power, but consider different values of the coefficient in front of it? So for example, things like y equals x squared. Let's say that's the coefficient 1. That's the one we've already seen. But then something like 3x squared or 5x squared or maybe 0.4x squared. How would these shapes look like together, right? So what would they be similar in some way, or would they be somehow different? Again, you can of course draw it by hand, especially by plugging in points, but we can also utilize our very handy tool of a graphing calculator here. So here is, notice how I've entered this function kx squared, where k is now my little slider, and I'm going to go to and from 1 for k, right? So kx squared, notice that I start off with k equals 1. So this shape right here is just x squared, my basic parabola. And as I increase k, the shape remains a parabola, but it is getting skinnier and taller and more stretched out vertically, right? But notice that no matter what k was, the general shape has always remained a parabola. Now, if I go below 1, so this is k equals 1, so this is x squared. If I go below 1, the opposite happens. The graph is getting wider and more shallow, yet still remains a parabola, right? So again, let's record what we found out here. So maybe let's draw ourselves another set of axes here. And what we've noticed was that if I start off with y equals x squared, again, let's just pretend that my drawing is actually a perfectly symmetric parabola. Then 3x squared is going to be a skinnier, taller version of the same parabola. 5x squared is going to be narrower and taller still. Whereas 0.4x squared, because the coefficient is less than 1, is going to be below my x squared parabola, right? So like this guy here, it's 1x squared. So 0.4x squared is going to be a parabola, oh wait, parabola that lies, oh my goodness, lies below my basic parabola, somewhere like this. There we go. Okay, 0.4x squared. Okay, so the general parabolic shape is going to remain, but how it is, whether it's shallow and wider at the bottom or narrow and tall, that's what the coefficient in front of it is going to dictate. I should point out that this review is going to be fairly fast in terms of power functions because this is some of the pre-calculus material. But if you would like to review it a little bit more, take a look at the pre-calculus review package sections that are mentioned on top of some of these slides. The link to the pre-calculus review package is available on the course syllable, and these are going to be the corresponding section in the package that will help you review all of these types of functions. There's exercises, there's more videos, there's suggested exercises and solved exercises with full solutions and examples. Okay, so let's take a look at what happens if we draw all of these power graphs on the same sketch, right? So far we've seen them one at a time, and we know that even powers are parabola shaped and odd powers are snaky shaped. So this graph has pictures of x squared, x cubed, x to the fourth, and x to the fifth. And I'm going to try to figure out which one is which. So from the previous discussion, we know that x squared and x to the fourth are going to be parabola shaped because it's x to an even power, which means that these guys are going to be shaped something like a parabola, something like this. So x squared and x to the fourth are either red or green, right? One of these two graphs is my x squared and x to the fourth. Whereas the odd powers, x cubed and x to the fifth, are going to be one of the snaky shapes, so either blue or orange. But the problem is, our analysis so far will only get us this far. I am so far unable to tell you whether the red or the blue graph is x squared. All I know is that the red or the green graph is x to an even power. So let's just see what happens as I draw these graphs on my sketch one at a time. Okay, so I start with x squared, and then let me add x cubed to the picture. Notice that first of all they intersect at 0 and then again at 1, but also notice that in the beginning, let me just erase this too, right? So once there's just a parabola, here the blue graph, which is the cubic, lies underneath the parabola up until the point of intersection at 1, and then above it afterwards. If I draw x to the fourth, note that in the beginning, near the origin, before the point of intersection, x to the fourth, which is my green graph here, lies even lower between 0 and 1, and then at 1 the situation reverses and it becomes the graph that is above every other graph. If I draw x to the fifth, it's going to be lower still, flatter at the between 0 and 1 near the origin, and then it's going to surpass everybody and grow fastest past the point of intersection at 1. So this pattern holds in general. We notice that, so if you just watch the parabola here first, look, if I start with the parabola and then I draw in other graphs, everything else near the origin will be below the parabola. And everything else after the point of intersection at 1 is going to lie on top of the parabola. So this is going to be true in general. If I am thinking near the origin, so between 0 and 1, then the smaller power, parabola being x squared, is going to be the function that is highest overall. So what we say in this case is that smaller powers, or power I guess, dominates. Dominates meaning it's the highest in the y value, right? So on this first piece here between 0 and 1, it is my parabola x squared with the smallest power that's going to be the highest on this region. In order to persuade yourself even more, it's probably a good idea to plug in some numbers. So I strongly encourage you to think about what if you plug in a number less than 1, let's say 1/2, and you compute 1/2 squared, 1/2 cubed, 1/2 to the fourth, and 1/2 to the fifth, let's say. And notice these are now going to be the y-coordinates of your points on the graph. So as you're computing them, notice which one of them is going to be the smallest and which one of them is going to be the largest. And you'll see that if the number you're raising to the power is less than 1, then it's the smallest power that's going to give you the highest actual number. Okay? Versus once I go past 1, it's going to be the larger power that dominates. Okay? So again, with the same idea in mind, try to plug in numbers like 2 squared, well, maybe not 2, just to be a little more interesting. 3 squared, 3 cubed, 3 to the 4th, 3 to the 5th. And notice that as the power grows, the value will grow, which is the opposite thing with the fraction that's less than 1. So what that means is I can look near the origin and I know that the smallest power is going to be the one that is the highest overall. So this graph is going to be x squared, the next one is going to be x cubed, the next one is going to be x to the 4th, and the lowest one is going to be the highest power available, or x to the 5th. So if I want to label them here, it's going to be x squared, x cubed, x to the 4th, and this guy is x to the 5th. Whereas after the point of intersection that we sometimes call the switch, the situation is going to reverse completely. So now the highest power is going to be physically the highest y coordinate. So here, the thing that's dominating in terms of the height is going to be the highest power. So it's going to be x to the 5th, x to the 4th, x cubed, and x squared being the smallest power after 1 becomes the one that actually is below everybody, all the other powers. Okay? So let's take a look at how that can help us when we have two different graphs, but they're not just power functions with coefficient 1 like we had here, but they actually have coefficients too. Okay, so we're going to sketch 3x to the 4th and 5x to the 7th, and we're going to find their points of intersection. Let's start with just a simple sketch and use what we've learned so far to guide us through what kind of shapes we're expecting to see and how many points of intersection do we actually expect to see on the graph. Okay, so the first graph I'm going to draw is 3x to the 4th. Now it's 3, so now we have a coefficient here. Notice that I have not placed any scale on the graph, and that is on purpose because I'm not yet interested in actual points. All I want to know for a first sketch is the qualitative, what is the general shape of my graph, okay? So there's really no need to worry about this 3 yet. This 4, x to the 4th, this 4 is of course an even number, which means that the general shape of 3x to the 4th that I'm expecting to see is a parabola. Okay, so I can sketch in 3x to the 4th as, oh wait, as an actual parabola here. There we go. Again, let's just assume that it's a perfectly symmetric parabola. This is the best I can do sketching freehand on a glass screen. This is my 3x to the 4th. Now the next one I want to sketch is 5x to the 7th. Now again, I don't have scale yet, so I'm not going to worry about this number 5. The 7th though dictates to me that because it's an odd power, I'm expecting a snaky shape like a cubic would have. But now the question is, where does that snaky shape live together with my already existing parabola, right? So I don't have a problem sketching here because there's no need to think about the interaction between my purple 3x to the 4th graph and whatever it is that I'm drawing now. But after the origin, I really have to think a little harder. Is my graph going to go like this because it's to the 7th, so it lives all above it? Is it going to go all below it because it's x to the 7th, so the power is flatter near the origin? Or is it going to do something in the middle like this, where it's first below it and then above it? Now, thinking back to our previous slide, remember that smaller powers have to dominate near the origin, but the larger powers will dominate further away from the origin, which means that because 7 is bigger than 4, near the origin, the 4th power has to be on top, which means that first my 7th power graph has to lie underneath the 4th power graph, but then after some switch point, which I've yet to find the coordinates for, the graphs will actually reverse roles, right? So this switch point here is also the point of intersection. And I noticed that overall, I'm actually expecting 2 points of intersection on these two graphs. I don't know what they are yet. I mean, one of them I can guess is the origin, that's pretty clear. But the second one I'll actually have to solve for algebraically. And in order to solve for points of intersection, I'm going to set my two functions to be equal and then solve this equation. Again, if you need more practice with how to solve these types of equations, take a look at the pre-calculus review package with the corresponding sections. And you guys are actually going to do this example, finish it off in class. I strongly recommend that for all types of questions like these, even when you're doing them on your own, to sketch the graph first, because it will establish an expectation of how many points of intersection you should expect, and that will help you double check whether or not you've lost anything in your algebraic manipulations. Okay, now after this video, you guys should be doing pre-lecture homework number 1, so please take a look at WebWork and do the corresponding exercises.